part is AC analysis, just like any transistor. Today the topic will be discussion of the DC biasing and DC analysis of JPEG. Since we already did DC analysis in our previous chapter, I expect that the JPEG DC analysis will be slightly faster. Nonetheless, I'll still talk about how to analyze the circuit. There are three types of bias mainly here. After completing all the bias, we will look at a few examples which are already worked out in the textbook, and I'll ask you to solve, pick a few students just like in every other class, and ask you to solve parts of a bigger problem. We finished until slide 21 during our previous class. Again, those of you who have not heard it in my last class, I intend to have your quiz 1 on December 28, Tuesday, during the class time. Instructions will be given before your quiz. It is going to be online. So we were talking about JFET, junction field effect transistor. One variation of FET is called a MOSFET, which stands for metal oxide semiconductor field effect transistor. Some of the characteristics of a MOSFET are similar to traditional JFET, and there will be additional characteristics which make them quite useful. We start with two types of MOSFET. One is called the D MOSFET and the other one is E MOSFET. The name D MOSFET comes from the fact that the first one is called the depletion type and the second one is called the enhancement type. Even though there are not really problems to solve, I usually not ask to solve problem with MOSFET. I focus mostly on JFET, but it's good to know about them. The first one, as you can see, is called a depletion type MOSFET or D MOSFET. Let me make it read more. See the construction, it is quite different from a regular JFET. On a regular JFET, you have either N channel or P channel, and then you have other type of material. Here, you still have the drain, gate, and source terminals. The dark black part are the ohmic contacts or metal contact, which behaves linearly in terms of voltage current relationship. The main body of construction, we call it the substrate. This one is made of a P-type material. Therefore, the large gray area is called the substrate and it's a P substrate. Also, you can see there's another additional terminal called substrate terminal, given by two capital S letters, SS. And then you see what happens. On the left-hand side, you have one N-type material joined with the ohmic contact to the drain. There's another N-type material at the bottom, the square shape, joined with the source with an ohmic contact. These two square blocks are also joined by a conducting channel. That's the N channel, same type of material. Between the dark black ohmic contact and the body of the MOSFET, there is a shaded area. You see, looks like a zebra pattern. This is a thin insulating layer of silicon dioxide. So two N-type regions are connected through an N channel, and N channel is connected to gate. So the top N is connected to drain, the bottom one is connected to source, the channel is connected to gate. But in between the metallic contact and the channel, there is the very thin layer of silicon dioxide. The whole N-type material along with the channel, they lie on the P-type substrate. So the basic construction is coming from the P-type. This is the depletion type. Next is the enhancement type. But before we talk about that, see, the symbols are quite different. You have N channel, P channel. For the N channel, the arrow goes inside. For the P channel, the arrow goes away. You have gate, source, drain. Sometimes you have a substrate terminal, sometimes you do not have it. It's an optional one. And unlike the JFET, there is additional vertical line. For the case of E-type MOSFET, there is a mistake in the slide. Can you spot the mistake? What is the mistake? Just stop here a few moments and then we can move on. Look at the construction. Again, based on a P-type substrate, you have gate, source, and drain. Two N regions. One is connected to the drain, the other one is connected to the source. And in between the substrate and the metallic contact, you have the thin layer of silicon dioxide. No channel. The top and bottom end are not connected through a channel. So where is the mistake? The mistake is in the text, where it says on the top, the drain and source connect to the N-type regions. The regions are connected via an N channel. The second line is a mistake from the publisher of this Pearson book. So please disregard this one. This one that I highlight in yellow, it is not true. Can I do a strikeout? Maybe there's a strikeout option. Highlight. Never mind, that is wrong. So how does the gate connect to the P-type substrate? There's a thin insulating layer of silicon dioxide between the contact and the substrate. No channel, it is correct. N-type materials lie on a P-type substrate. They may have the additional terminal. So again, the substrate terminal, which is SS, this one is optional. It may be there, it may not be there, but you definitely need the three terminals, gate, source, and drain. Those three are must. Any questions? Do you have any questions? Can I move on to the next part?
Teacher, can you explain it again? Like, what
Which
is a
part?
mistake of the textbook?
The mistake is not in the textbook. It's actually the slide, the one that is provided to me, but by the publisher of this book. You see in the picture between the top and bottom end, there is no channel. This is the E-type MOSFET. The D-type MOSFET has an N channel, long, thin N channel. This one does not have a channel. It should not have a channel. But the text slide writes that they have a channel. That is the mistake.
Okay,
No channel.
So the text should say no channel, isn't it?
Yes, the text should say no channel. As you can see, it says there is no channel. This statement is correct in the middle. The second line is not correct.
So they are not connected. Okay.
No, they don't connect through a channel for the E MOSFET.
Okay, got it.
So for E MOSFET, see, there is a slight difference in symbol. The D MOSFET, the second vertical line, it's a continuous line. For E MOSFET, it's a broken line, like a dashed line. Again, if the arrow is going inside from the substrate, it is N channel. If it's going away from the substrate, it is P channel. Sometimes you have the substrate, sometimes you do not. But basically, you have three terminals as a minimum. If you are handling MOSFET by yourself in the lab or in the factory, you have to be extremely careful because they are very sensitive to static electricity. Here, if you go back to any of these, the layer, the insulating layer of silicon dioxide, which is right here, this region, this layer is so thin in construction that if you have even a little bit of static electricity discharge, which often comes from people's bodies or another object, it will create an unwanted current conduction inside the MOSFET. And it can be large enough, even though the value is small, but that small value already is large enough to damage So you have to protect, you have to use protection when you handle MOSFET. There are certain special bags which neutralizes or they protect from static electricity. Those are called static sensitive bag. Always transport in that special bag. If you are handling by hand, you have to wear a static strap. Those who work in the semiconductor manufacturing, inside the room where the semiconductor is handled and processed, it is called a clean room. So they wear clothes like astronauts. Not even your hair can be exposed. Even small dot of sand or dust, it can destroy and damage. And if you are handling MOSFET, then you will wear additionally a static strap. Sometimes you can do some protection between the gate and source. You can connect a back-to-back zener in order to limit any voltage and current. So you just create basically almost an open circuit condition where it will not pass any current. Different ways of protecting your MOSFET. There's another one called vertical MOSFET. The structure is a bit different. See, there's a whole N substrate here. And then the black ones are metallic contacts. You have P. What are the advantages? A vertical MOSFET provides a greater surface area for conduction. You have more carriers. For an N channel or N substrate, you'll have more electrons that can take part in conduction. If you have a P substrate vertical MOSFET, you can have more holes. The lack of electron we call holes instead of calling protons. So more particles participating means more current conduction. Remember the JFET or MOSFET, the field effect transistor is not, it's a unipolar device. Not both electron and hole participate, either electron or hole, depending on what type of substrate you have. For the BJT, it's bipolar. Electron and hole, they both participate in current conduction. So what are the advantages of BMOS? It can handle higher currents because of more surface area available. If you have more surface area, what happens? Any heat that is generated due to electricity conduction, it can dissipate away fast. If you're trying to, say, drink from a mug a very hot coffee, when you try to drink, sometimes you burn your mouth. If you actually pour from the mug to, what do you say, a saucepan or a small bowl, and then you try to drink from there, you'll see it's not hot enough, so it's comfortable. What happens because of the larger surface area, the heat is now spread over, so the heat density is less, which means heat goes away faster. The biggest enemy of any electronic device is heat, which I learned the hard way. That's why recently I had to change my laptop battery. Now I make sure that I always operate the laptop in room temperature, maybe in air condition, and then I don't always charge it, and I avoid overheating. Heat damages and destroys electronic devices. Switching time is faster than the regular MOSFET for BMOS. Then there's another one, complementary MOSFET, CMOS. This one, see, it uses a P channel and N channel in combination. But the peculiar thing about this one is often on the same substrate. The whole rectangle is the base structure. The light blue part is N-type substrate, and then you have a combination of P and N-type material. In between, they are joined through a channel. If this one is on, it becomes a P channel MOSFET. If this side is on, it becomes an N channel MOSFET. Due to different input voltage connection, you can turn one side on and the other side off. We do not have any mathematical problem to solve from the MOSFET, not in this course. What are the advantages you can use in logic circuit logic gate design? Input impedance is higher. If you have higher input impedance, it helps to suppress noise. Not easy to pick up noisy signals, which you do not want as well. Switching speed and time is faster. Operating power required is low, which means less heat generated during the operation. But in both cases, you can see the thin layer of silicon dioxide is there, which is given by the dashed, the angled dashed line. It's like a thin wafer. That's why no matter what type of MOSFET you are handling, you always have to be careful. So that was the discussion of the basic construction of MOSFET and JFET. Now we are going to biasing. Do you remember what is the definition of biasing? In the case of an amplifier, how do you define biasing? Think about it for a few moments and see if you can actually tell me the meaning of biasing. Who remembers? No
What did you
one?
ask again?
I asked the definition of biasing. What is the meaning of biasing in this context that we are asking? No one?
Applying an external voltage.
Okay, that's kind of okay, but it's quite vague. So you have to be more specific. For the case of an amplifier, biasing means applying a DC voltage in order to turn on the amplifier so that it can amplify signal. What is the meaning of signal? A signal is an AC wave, and the DC source is biasing. When the amplifier is amplifying, actually it is not, the end goal is not to amplify the DC. The end goal is to amplify the AC signal, either in terms of voltage or current by means of gain, but it cannot do that without being turned on. You need DC to turn on and create power transfer. The average power of an AC signal is 0 because you have a positive peak and the other one is a negative peak. So power transfer is happening from the DC sources. That is biasing. What are the biasing circuits we studied here in BJT? 4 biasing circuits, remember? Fixed bias, emitter stabilized bias. Then the third one was voltage divider bias. And what was the fourth one? Collector feedback. These are the 4 bias type circuits I showed you in the BJT class. For the FET, we study 3 types of bias, DC bias mainly. You have fixed bias, and another one is called self bias, and then you have voltage divider bias. For the case of fixed bias, before I actually start talking about it, I have to tell you, I think I should tell you, there are 2 types of solution possible. The first solution you can do totally mathematically for fixed bias. You don't have to draw a graph at all. You can also do graphical solution by drawing the characteristic graph, finding the Q point, all those things. If you go to self-bias, I'm afraid it is not possible to do completely mathematically. You actually should draw a graph and see where is the Q point or the operating point. And same Same condition applies to voltage divider bias. Complete mathematical solution, you cannot do it. You have to draw something. So let's go look at the fixed bias then. Fixed bias cell voltage divider. This is for JFET. When we study biasing, in this course, we do biasing only for JFET. If you are curious, if we are using a D-type MOSFET, you can use self-bias and voltage divider. For an enhancement type, it is possible to do two types, feedback and voltage divider, which are the most common one. Just like BJT have some basic equations, the JFET also has basic current relationships. What is collector current for BJT? IC equals what? What's the equation? Do you remember the equation for BJT? No? What is the equation for the collector current in BJT? How come you don't remember?
When you say collector current,
Yes, IC. What is IC? What is the equation for IC for a bipolar junction transistor? I'm not talking about JFET now. I'm just trying to see if you remember the previous one.
is it? Wait, this is my guess. Is it beta IP?
Beta IB, yes, that's the equation. That's what I'm asking about. IC equals beta IB, right? And IE equals IC plus IB. So that's the relationship which you always have to remember. For the case of JFET, what happens? There are also some assumptions and basic equations. First one is IG equals 0. The gate current equals 0. Why do you think they make that assumption? IG is 0 due to what? The JFET is a high input impedance device, so on the input side you have a high impedance, the unit of which will be ohm. A high input impedance is often approximated as a open circuit, right? So when the circuit is open, the current really cannot flow, or whatever flows, it is so negligible, you can say IG approximately 0 ampere. The second approximation, ID equals IS. The drain current and the source current, they are pretty much the same. Why? If you remember the JFET or any field effect transistor, if you remember how it's constructed, there's a channel, whatever coming out of the drain or source going through the drain is the same current, so ID equals IS. And then the third one is the very important one, JFET and D-type MOSFETs, this is their characteristic equation. ID equals IDSS, which is saturation current at pinch off, times 1 minus VGS over VP whole squared. It's a voltage control device. The output current will depend on the input voltage, gate to source. Whatever you do that to gate to source voltage, that controls your output. So it is a voltage control. For an enhancement type MOSFET, there is a special equation, K times VGS minus VT square. We don't use this equation in this course or any of the problem. This one you can ignore. But if I have time, maybe during a review class, I will show you an example of a MOSFET problem solving. Here T refers to a certain temperature, usually expressed in degree Kelvin. And K is a term associated with the material parameter. First circuit, fixed bias. We are in the first biasing circuit. My intention is to complete all the biasing circuits first, and then we look at maybe 3-4 examples. The DC source is here, VDD. Then you have a drain resistor RD. This is drain, gate, and source. Between gate and source, we apply a voltage, another DC voltage, VGG. You can notice the polarity. And just like for BJT, which has a voltage drop VBE, there's a voltage drop between VGS, but it is not a fixed value 0.7. VBE is 0.7 volt. VGS, you know, it can be 0 or it can be a negative value, which we have seen in the previous class. In this type of problem, the values of IDSS and pinch-off voltage are usually given. Also on the spec sheet, these are given. Let's solve the loops. So on the outer loop, VDD minus IDRD minus VDS equals 0, which means VDD minus IDRD equals VDS, the voltage from drain to source. There are also two mistakes, I think, in this slide. If you can tell me before I ask, that is very good. What is VS? The source terminal voltage, what is it? The source terminal directly on the ground, so VS is 0 volt. VC is VDS? No, it is not VC. Actually, here is the first mistake. It is not VC. It should be VD. Because VDS means VD minus VS, and VS is already 0, so VD is same as VDS. In between, there is nothing. What is another mistake? Here, it should write VG. VG equals VGS, because VGS means VG minus VS. VS is 0. If you put a probe here, it is also VGS. And then VGS equals minus VGG. The last one is correct. What is the loop equation for the closed loop? VGG plus VGS equals 0. I'm taking from the first sign, or you can say minus VGG minus VGS equals 0. Therefore, VGS is what? Minus VGG. So VGS is a fixed value. Let's say the battery is 3 volt, but you can see it is minus and plus. Polarity is minus plus, which means in this case VGS is minus 3. Is this part clear? Is this part clear to you?
Yes, sir.
VGS, this is why it's called a fixed bias. And you don't
teacher?
even have to draw a graph. Yes,
Can I ask you something?
go ahead.
Where did you find the VG on the plus sign?
This one,
Yeah, the VG.
VG. See, the slide was missing VG. VG is like this. If you use VGS, let's say VGS, using the double subscript notation, what can you write? VGS means VG minus VS, right?
Mm-hmm.
VG, let me write inside minus and then VS. What was VS? Is 0. So this term is 0. So in this case, VGS and VG, they are the same at this point.
Okay.
Because of the fixed bias, you know VGG is negative VGS, or VGS is the negative value of whatever volt you put here. In the problem, IDSS and VP is given. You don't even have to draw the graph. You know IDSS from here, you know VGS, VP is given, so you can actually solve for ID. Once you know ID, you can then know what is VDS, because VDD minus ID RD. No need to draw a graph, but you can also draw a graph. Today we'll see both approaches. After fixed bias, the second type of bias is called the self bias. Now there's a difference. In the self bias, you have resistors on all the terminals. First, this is VDD, your DC bias. You have drain resistor RD. You have the gate resistor RG. You have source resistor RS. And this is the input AC signal. So it will be like this. Output signal may be amplified. But when you do the DC analysis, do we worry about the capacitor? No, we do not worry about the capacitor. What do we do to the capacitor? In DC analysis, how do you treat the capacitor?
You short it?
No. Short for AC. DC analysis open circuit. Means capacitor, you don't get the AC signal in, you don't get the AC signal out. So you forget about capacitor and whatever is beyond the capacitor. Now, let's analyze the loop. For outside loop, VDD minus IDRD minus VDS minus IDRS equals 0. If you just take the loop, VDD minus IDRD minus VDS minus IDRS is 0, because ID equals IS. And this is plus minus VDS. Do not forget this voltage drop. You always have to put this in the equation. That's the Kirchhoff's voltage law. Here is an interesting part on the input loop. What is the assumption of IG? We approximate IG to what? What was the approximation? Only 2 slides ago we talked about this. For JFET, what is gate current equal to? Can you not remember? When you have high input impedance at the gate, what would be the current approximately? Okay, this is rather disappointing. We just talked about it like 5 minutes ago. IG is 0. If 0 current passes through this resistor RG, what is the voltage?
0 volts.
Yes, Ohm's law, V equals IR. RG multiplied by IG, which is 0. This is 0 volt. If you have 0 volts across a resistor, it is like a short circuit. So you can replace or approximate RG as a short as if it is not there. And then the loop equation became what? This is plus minus. If you look inside the loop, the clockwise loop, I can say, again, this is plus minus V of RS. V RS. Let's write that. VGS plus VRS equals 0, or you can say minus VGS minus VRS equals 0, which means VGS equals what? Minus VRS, negative VRS. And what is V of RS? According to Ohm's law, it is ID times RS, right? The voltage drop is the current times the resistor. If VGS equals negative VRS, means VGS is actually, you can write this equation, VGS equals minus ID times RS. Sorry, it's a bit messy here. I hope you can see. So as you can see, RS is a fixed value, but ID can vary. Depending on different level of ID, you can have different VGS. That's why you cannot use a fully mathematical solution. You have to draw the graph. Here, self bias, we actually derive the equation now, VGS equals minus ID RS. So you have to pick a value of ID. Let's say your IDSS is 8 milliamp. Start with a value of ID which is less than the saturation current. Maybe start with 1 milliamp, okay? 1 milliamp, and let's say RS is 1 kilo ohm. So what is VGS? 1 milliamp times 1 kilo ohm is
1 volt.
And this is a negative, so negative 1 volt.
Negative ohm.
Yeah, this is, I'm drawing a curve. So when ID is 1, VGS is negative 1. Your dot is here. Let me zoom. And try with a few other values before you reach IDSS. And then this is 1 and 1. VGS. This is VGS. And this is ID. The axis is like this. When now RS is 1 kilo ohm, it doesn't change. ID is 2 milliamp. RS will be 1 kilo ohm. So VGS is 2 times 1, and negative is negative 2 volt. Negative 2 volt is here. When ID is 3 milliamp, VGS will be negative 3 volts. 3 times 1 kilo ohm and minus 1, 3. So you found 3 dots or even 2 dots. You can use a scale. When VGS is 0, when ID is 0, VGS is obviously 0. You can see it on the equation. ID is 0, VGS is 0. That's your first point. Your first point is in the center. If you take a scale now or a ruler, join the straight line. Okay, let me draw a straight line. You have a straight line. What is this line called? It is the load line that is coming from the circuit. But you need something else. What do you need? You need the characteristic graph, which let's say IDSS is right here and pinch off voltage is here, and in the middle you have whatever, which you have to draw. What we'll do, let's try to draw a curve just like this. Okay, that's good enough. When the load line intersects the characteristic graph, what do you call this point? Q point, isn't it? The operating point. And now you project a line from Q point. This is the operating drain current. This is the actual current that is flowing. So this we will write IDQ. And if you project a voltage here, project on the voltage, this is VGSQ. And then you have to use the operating point values of voltage and current in order to calculate everything. Any questions? So the straight line you plot using this equation, VGS equals negative IDRS. That is the load line. Then you have to plot the transfer curve using the equation. By the way, I did not tell you in my first class, quite important. The name of this equation, also known as Shockley equation, named after William Shockley. So sometimes I say, give me the Shockley equation of JFET. This is what I mean. Now you have to plot the curve, which is not a straight line, using the Shockley equation. I taught you the shortcut points, right? When VGS equals VP, and then when ID equals IDSS, and when ID equals half of IDSS, when VGS equals half of VP, you can plot 4 points and draw a smooth curve. We'll do examples today, don't worry too much now. So what about the equations then? See, the Q point is located where the first line intersects the transfer curve. Using the value of ID at the Q point means now you have to use IDQ. VDS is VDD minus this ID is IDQ times RS plus RD. You have two resistors now. What is VS? VS is from this to this. It is IDRS, simple Ohm's law. What is VD? You can say VDS plus VS because VDS means VD minus VS. So if you found VDS, add VS, you can find VD right here. Or you can take the voltage drop from top all the way to here. You can write VDD minus ID RD, means V of RD. Voltage drop from the DC bias to the voltage of the RD resistor. Any questions? Is this one clear?
Yeah, for me now.
What about the rest of the class? You are quite silent most of the time. I hope you understand.
Yes, done.
Okay, very well. Then there's one more bias. And then we'll go to actual examples. I don't want to go to anything else. Maybe we finish a bit earlier today. I don't know. I don't want to start any AC analysis. Just focus on this one. Voltage divider bias. You may be remembering this from your BJT voltage divider. The BJT voltage divider is a bit complicated. Why? There are two ways of analyzing. One is called the exact analysis, Thevenin, and the other one is called the approximate analysis. When beta RE is greater than 10 times R2. Here we don't have beta. See, we always approximate IG 0 ampere because of the high input impedance. Can you see well when I'm drawing?
Yes.
So it means it refers to this junction. At this junction, the current that's coming out of the source, it sees a high input impedance. It is a barrier, it's an obstacle for the current. So the current does not go here. If you think IG goes here, no, it does not go. Let me erase this one. Which means the current that's coming from the source is actually passing through R1, and instead of at this junction you expect that some will go here, but it's almost zero. So instead of going to the right hand side, it will come to this junction in between R1 and R2, and then it will pass through. If you want to find VG at this point, what is VG? What equation can we use? See, here's a voltage. Two resistors. At a junction, it gets divided.
Voltage divider.
Voltage divider. So VG is VDD times R2, because VG is measured from top of R2 to the ground. So we are measuring basically the R2 voltage. VDD times R2 divided by R1 plus R2. Also, we are doing DC analysis. Capacitor is open, do not worry. Means capacitor, we don't have to worry now. Output side equation, what is that? VDD minus IDRD minus VDS minus IDRS equals 0. So let me also put here plus minus, this is VDS, D and S, and definitely think of plus minus VGS. VGS. If you look at the inside loop, VG minus VGS minus IDRS equals 0. Isn't it? Is that correct? This loop, let me read again. VG minus VGS minus IDRS equals 0. The polarity is like this. Because the voltage drop across RS is IDRS. From that equation, what is VGS then? VGS will be VG minus IDRS. 1 second. Next slide. Actually, go to next slide first. Because you are right, it's a voltage divider. IG approximately 0 amp, no current is going. So all the current is passing through R1 and R2. At this point, VG is given by the voltage divider equation, VDD R2 over R1 plus R2. And the Kirchhoff voltage law is this: VG minus VGS minus IDRS equals 0. Therefore, what is VGS? It is this. So if you have a positive voltage VDD and you have R1 and R2, the value of VG is something that is fixed. You have to find it first. Is it a positive value or a negative value, you think, for VG?
Can you repeat the question?
What will be the value of VG? Is it a positive voltage or a negative voltage? Always a positive. If you put a positive DC bias and resistor values are positive, this is a positive value. So what is the Q point? Okay. Look at the equation at the bottom. When ID is 0, what is VGS?
It will equal to VG.
Yes. When VGS is 0, what is ID?
Positive.
Yeah, what is ID in the equation? When VGS is 0, what is the current ID? I think it's VG divided by positive VG divided by RS, isn't it?
Yeah, VG divided by RS.
Yes. So how will you draw the load line? Here is how to draw the load line. You know the equation? VGS equals VG minus IDRS. When ID is 0, VGS equals VG. This is your first point. When VGS equals 0, you correctly said that ID equals VG over RS. So take the value of VG. How did you find VG? You already found it. VDD times R2 over R1 plus R2. And you divide by the resistor. Let's say this is the point. If you join 2 points with a straight line and keep extending all the way here, you can actually get a straight line. That is your load line, depending on the circuit, the network. And then you take the Shockley equation, ID equals IDSS times 1 minus VGS over VP whole squared, right? You draw this curve. The curve intersects with the load line. And at this load line, what is ID? That is the ID value that you will use to solve the circuit. And this is the VGSQ, which you'll use to solve the circuit problem. Voltage divider bias calculation. So did we do the outside loop? I think yes. VDD minus IDRD minus VDS minus IDRS equals 0. Therefore, what is VDS? It is VDD minus ID times, in the bracket, you add the two resistors. Remember, this ID is IDQ that you have solved using graphical means. You cannot solve mathematically. No. What is VD? VD is just here. at this point was the voltage drop. You can say VDD minus IDRD. You can also say the last one is Vs equals IDRS, which is correct. Vs is from terminal S to ground, so it's the voltage drop, IDRS. Now we are actually ready to look at some problems, but just before going there, let me tell you, if you have P-channel FETs, we are all doing N-channel. The same calculation and graph are used, but the voltage polarities will be reversed. The current directions will be reversed. The graphs which you get for a P-channel will be mirror image of the N-channel graphs. That's what I wanted to say. And applications for field effect transistors, some of these are the applications, but let's look at some examples and problems by switching the screen. Your Teams page is here, class notebook. I already put a few materials there in the collaboration space. Let me get the students list. Okay. First of all, try a fixed bias example. It is a worked out example in your textbook. And let me enlarge the picture for you. In the following network, determine the 6 values. I continue with the person which was after the previous person. So is Siripop here?
Yes, sir.
Siripop, you will be telling us A, part A.
Okay, sir.
VGSQ. Is it large enough or I should enlarge more? I think this is good. Bottom is the ground. If you don't see it, the bottom is the ground. V2.
Yes, sir.
You will be doing part B, IDQ.
Okay, sir.
And Mr. San An, you will be telling us, San An is here, VDS, drain to source, VDS, part C. Waramet.
Yes.
Part D, VD.
Okay.
All right. And part E will be for Miss Navawan, VG. Is Navawan here? Navawan? Maybe she's not here. How about Natapop?
Yes, Ajahn.
You'll do part E, VG.
Okay.
And the last one is for Warapat.
Okay, yes, sir.
Okay. And along, everybody can work, try to figure out how to find it. Now I ask you to do mathematically. And I'll keep talking along the way. So it's a fixed bias. You see, there's a battery inside. The battery inside the loop. The equation is VGG plus VGS equals 0. You can find what is VGSQ. Who was doing VGSQ? Siripop.
Hey, teacher.
Yes.
Yes, teacher.
Like how do we know like which one is VGSQ?
In the fixed bias, VGS is a fixed value.
Mm-hmm.
So that is the operating point. You see, we studied the first bias circuit. In this circuit, what is the equation? VGG minus VGS is VGG plus VGS equals 0. So whatever VGS you have, that's a negative VGG, and that is the operating point. It is fixed. That's why it's called a fixed bias. This
It
is,
should be -2.
yeah, it is -2 volt. This is the only case where you can do only mathematically without drawing a graph. This is the only type of bias for JPEG. And for part B, how will you find IDQ mathematically? IDQ is coming from the equation. It will be like this. ID SS times 1 minus, you have to use VGSQ, the operating VGSQ over VP, and then what? Whole squared. One word of caution. If you have a minus sign, put a minus sign here. VP is a minus sign, put a minus sign. Do not miss the signs. If you miss the plus or minus signs, you will be ending up with the wrong answer. VP is given, pinch of voltage is given. So if you take -2 divided by -8, minus and minus cancels out. It is 1 minus 1/4. IDSS is given. Also notice the unit, 10 milliamp. Do not forget that there is a milli. What should be the value of IDQ? 1 minus 0.25, 0.75 square times 10 milliamp. You should get 5.625 or 5.63 milliamp.
Teacher, can I
Yes.
ask one question to be sure?
Yes.
Like IDQ, like it is the same like ID, right?
Yes, IDQ is same as ID.
Oh, okay.
The word, the letter Q means the operating point, Q point. So what is the actual ID and what is the actual VGS at the operating point? That is what they're asking.
Ajahn, so B, I got 5.625 milliamp.
5.625 milliamp, yes. If you put all the values here, it is 5.625 milliamp. So this one is, after you find IDQ, what is VDS? You can say VDD minus ID RD. This is RD. This terminal is the drain terminal. So this is RD. The equation is VDD minus ID RD minus VDS equals 0. So VDS will be VDD minus ID RD because S is on the ground. What is VDS? 16 minus, you multiply 2 kilo ohm with 5.625 milliamp.
Ajahn, I got number 3
Yeah.
equal 4.75 volt.
4.75 volt. Very well. And then that's correct answer. 4.75 volts. Somebody was doing number 4. Waramet was doing number 4. What is VD?
VD equal VDS, I think.
Yes, correct. In this circuit, VD is same as VDS. If you take VDD minus IDRD, same value, 4.75. Who was doing a VG? Number 5?
VG equal VGS.
VGS?
Yes. -2.
Okay, let me see. VG minus VS equals VGS. I'm just verifying the equation. And VS is on the ground, so VG is VGS, -2, correct. The last person was Warapat, right?
Yes, Ajahn.
What is VS, Warapat?
I got a very weird. What are you?
VS, the last one.
Yes. Yeah, I got it very weird.
What is the weird one?
I got like 5,625 volts.
Huh?
Yeah, so
No,
I'm
look
checking
at the S. Look at the S. You don't even have to like calculate. It is on the ground. VS is 0 volt here. You can straightforward say VS is 0 volt. We don't have we don't have any resistor on the source terminal. If there's a resistor, you can say VS is actually IDRS. I think you are trying to find IDRS, but there is no RS.
I thought 1 mega ohm is an
No,
RS.
that is the input RG. Sometimes you may have 1 mega ohm or you may not have anything. This is RG. And since gate current IG is 0, we approximate the voltage drop. 0 times RG, 0 volts, and then short. This is an approximation. But really, that is RG. It is not VRS for sure. So this was a purely mathematical solution. There's a graphical solution to this. I'll show you the graphical solution, how it is done. For the graphical solution, what did we find from the circuit? What did we find? VGSQ is -2 volt, right? So you already know what is the Q point. VGSQ, -2 is a fixed value. If you draw a straight line, straight up, the black line, you have to intersect the characteristic graph. This one you have to actually draw. In our problem, IDSS is 10 milliamp. VP is, pinch of voltage is -8 volt. So we can take the 4 shortcuts or 3 shortcuts. When VGS is 0, what is ID? ID equals IDSS. VGS is 0, ID equals IDSS. That's your first point. When VGS equals VP, what happens to the equation? ID becomes 0, this point. And then at VGS is VP over 2, which means -8 over 2 is -4 volt. ID will be 1/4 of IDSS. 1/4 of 10 milliamp is 2.5 milliamp. This is the point. Another shortcut you can draw. Some people can draw curves with 3 points quite smoothly. For the best curve, you can have another point. When ID equals half of IDSS, which is 5 milliamp, what is the value of VGS? 0.3 times VP. What is 0.3 times -8? -2.4. So see where the point intersects. At 5 milliamp, it is around here, -2.4. And then if you join all the curves, all the lines smoothly, you have this curve. From this curve, you get IDQ, because this is the Q point, 5.6. The mathematical solution was 5.625. And VGSQ is 2 volt. You know it already. And then once you find IDQ, you can solve for VD, VDS, etc. All the other parameters that you have been asked. Any questions about this one? Are there any questions? No questions?
I don't have.
Okay, after fixed bias, the next one we studied was self-bias. For self-bias, we actually have to draw. It needs, I wrote it, it needs both graphical and mathematical steps. You cannot do everything by using mathematics. What is VGSQ? If you remember the equation for the self-bias, VGSQ is minus IDRS. That's the equation. VGS equals minus IDRS. We have not found VGSQ yet. Thankfully, in this problem, RS is 1 kilo ohm. So I actually know what the graph will look like. Right? When RS ID is 1 milliamp, VGS is negative 1 volt. ID is 2 milliamp, VGS is negative 2. So this is the graph. For 1 milliamp, negative 1. 2 milliamp, negative 2. So you actually draw a straight line all the way up to there. And then you have to draw the characteristic graph here. IDSS is 8 milliamp, pinch off voltage is negative 6 volt. Let's see how the characteristic graph is drawn. When VGS is 0, ID equals IDSS 0.1. When VGS equals negative 6, means VGS equals VP, what is ID? I'm remembering the Shockley equation, 0.2. When VGS equals half of VP, means negative 3 volt, the current is 1/4 of IDSS. 1/4 of 8 milliamp is 2 milliamp. 2 milliamp is right here. Should I increase or can you see? 0.3. If you want to draw a beautiful curve, you can also take 0.4. When ID equals half of IDSS, which means 4 milliampere, VGS will be 0.3 times VP. 6 multiplied by 0.3. Negative 6 multiplied by 0.3 is negative 1.8. As you can see, if you draw, it is kind of negative 1.8. It is right here. So once you join this, you have a curve, the characteristic curve. This is shown separately, but you actually have to draw everything together. And if you draw a curve and then you draw this load line using the equation VGS equals minus IDRS, the end result will look like this. See where are the Shockley curve? Here. Here's another one, and for 2 milliamp and minus 3 volt is right here. Join the load line. It is a straight line with a negative slope because you can see VGS is minus IDRS. ID equals what? Negative VGS over RS. So Y equals MX, but it's a negative slope. Once you intersect, now you can find IDQ. Before COVID, the students would draw in the class on the board. That is, I can't even remember when, 2 years ago. And the VGSQ would be found around negative 2.6 volts. This will solve for part A and part B. Let me write the values for you. Negative 2.6. V IDQ was it 2.6 milliamp? Yes. 2.6 milliamp. So what is then VDS? VDS how much? It is VDD minus IDQ times RD plus RS. Can we all calculate? Can you see the picture? No, maybe not. Try to increase. Okay. What is VDS? 20 minus, in the milliamp you have 2.6 multiplied by kilo ohm. Actually totally is 4.3 kilo ohm. What voltage do you get for VDS?
8.82 volts.
8.82. Okay, that's correct. Yes. Then let's calculate VS. VS is here. This is V. So what is the V from top to bottom? It is IDQ times RS. VS will be, I think, 2.6 milliamp multiplied by 1 kilo ohm is 2.6 volts. VDS is 8.82 volts. 8.82. VS will be 2.6 volts because that's 1 kilo ohm. What about VG? In this loop, VG is VGS. If you write VG minus VS equals 0. Sorry, no, VGS. What is VG? It is VGS plus VS. You see VGSQ is negative 2.6. VS is plus 2.6. What happens to VG? 0 volt. Is it correct? Yes, it's correct. Why? Because of the approximation IG equals 0. IG approximation is 0. So what is the voltage drop here? IG times RG, what is it? 0 volts. We approximate the resistor with short. VG, the probe is measuring from G to ground, so VG is 0. What about VD, the last one? VDD minus IDRD. 20 volt minus 2.6 milli times 3.3 kilo ohm. You should get,
Sorry, Natija.
yes,
So VD.
VD, last one. What is VD? VD is,
Oh, never mind.
I'm drawing a blue arrow right here.
Mhm.
VD is not same as VDS now, because now you have a resistor between S and ground, so it cannot be same as VDS.
I got 11.42.
Yeah, 11.42 volts. Here it will be, I write 11.42 volts. You can verify 11.42 minus 8.82 minus 2.60. Yes, I just verified the loop. So 11.42 is correct. That's why this one you cannot do only by equation. The Shockley equation is for this part. The load line equation is for the left hand side. You draw on the same graph. If you draw the load line here, this is your end result, and this gives you the answer for IDQ and VGSQ. Then use the loop equation to solve for the rest. Similarly, we have another example. We may not be able to finish today, but if not, then we'll continue on in the next class. I kind of drew it here, so many things for you, but in the next class, maybe we can start again with a complete clean slate. For the voltage divider equation, voltage divider bias, what is the equation? VG minus IDRS, right? When ID is 0, VGS equals VG. How are you going to find VG? Voltage divider, 16 times 2, what was it, 220? Can't remember. I'll clean it. For the next class, I'll clean it. Or let's clean it now. 270, see? $16 times 270K divided by 2.1 meg plus 270K. Whatever that is, it will be your VG. We'll do this problem in the next class. But I'll show you the hint. This is VG. Right? And then when VGS is 0, what is ID? It is VG over RS. VG over RS, it turns out to this point, the black point. You join the line and then you extend. At the same time, you have to draw the blue curve, the Shockley curve, with the information IDS is 8 milliamp and VP is negative 4 volts. So with the 8 milliamp and negative 4 volts, I'll also erase this one. Keep it for the next class. VGS is 0, ID is 8. VGS is negative 4 volt, ID is 0. What else? VGS is half of VP, means negative 2 volt. It is 1/4 of 8, means 2 milliamp and negative 2 volts. You want to draw another curve? ID equals IDSS over 2. So at 4 milliamp, it is 0.3 times VP. 0.3 times minus 4 is negative 1.2, around here. You draw the Shockley curve, and from this equation, you draw the load line. It will intersect. You can try with the graph paper in your hand at home, which will give you the value of IDQ and VGSQ. Once you find that, rest is all simple. Do not worry about the capacitor because DC analysis capacitor is open. Same equation, what is VDS? It is VDD minus IDQ RD. The loop equation is like this. VDD minus IDQ RD minus VDS minus IDQ RS equals 0. Therefore, VDS is VDD minus IDQ times RD over RS. What is VDG? This one is asking a rather weird thing. VDG. Nothing to worry. Why? How can we write in double subscript notation? VDG. It will be what? VD minus VG, isn't it? VD you can find. It's VDD minus IDRD. You will find VD. What is VG? You already found in the beginning. VDD R2 over R1 plus R2. So you can find VDG easily. Let's do it on the next class. It's almost time for me to take your attendance call. Today is December what, 9? Balang? Is Balang here? Can you still hear me?
Yes.
Okay. I don't get response from Balang. Tirabut?
Yes. Sorry, sir. Balang here, sir.
Balang. Okay. Napatra?
Yes.
Pakon?
Yes.
Raje?
Yes, Ajahn, I'm here.
Sonikan?
Yes ค่ะอาจารย์
Michelle?
Yes ค่ะอาจารย์
Phil?
Yes, I'm here.
Silicon?
Yes อาจารย์
Wisalut, he already mentioned that he went to vaccine, so I just give him credit for that. Yu Cheng?
Yes, teacher.
Sisihang? Sisihang? Is Sisihang present? Patampong?
Here ครับ
Kungsu?
Yes, sir.
Martin?
Yes, Ajahn.
Kolawit?
Yes, Kalawit here.
Pichayut?
Yes, ครับ
Jima?
Yes, sir.
Suanyuan?
Yes.
Satawat?
Yes.
Yapeng?
Yes.
Seni?
Yes.
Siripop?
Yes, sir.
Pitu?
Yes, sir.
Sanan?
Yes.
Sanan is present. Boramet? Boramet was present, right? I talked to you today. Nawawan?
present
I was calling you for solving problem. Nawawan, next time I'll ask you next week. Nathapop?
okay
Yes, Ajahn.
Warapat?
Present อาจารย์
Nataya?
Yes teacher
Pichayapon?
yes sir
Komchan?
Yes, Komshan here.
Hiradon?
Yes, I'm here.
Kitsanapong?
Yes, right here.
Atitya?
Yes.
Hasin?
yes
Sukaina?
Yes
Sirin?
Yes, teacher.
Min Luin U? Absent Min Luin U. For the assignment, I returned the first assignment. I picked 20% of the student from the class randomly, and I looked at your work and I checked. I found only some small mistakes, so I put the comment when I returned. You can find in Microsoft Teams and also look at the solutions. For assignment 2 is due on December 14. You have time until end of December 14. See you next week.
Thank you, Dad.
Thank you, teacher.
Thank you,
welcome.
sir.
Thank you, teacher.
Okay.